In this video, we're going to talk about scalar and vector projections. Referring to the diagram below, the scalar projection of vector A on vector B is obtained by drawing a line from the head of A perpendicular to B. And this little shadow that's created is the scalar projection of A on B. We have it indicated in red. Now, sometimes that vector upon which we're projecting might not seem long enough. So what we do is we, as shown in the right-hand diagram, extend the floor if necessary. Almost sounds like cheating when you hear it. But we extend that floor if necessary, and now we have a scalar projection as shown. Okay? Now, if we wanted to determine a formula for the scalar projection of A on B, we could say that the cosine of theta is equal to the scalar projection of A on B, which is the length of this line, over the magnitude of the vector A. That's like saying cos theta equals adjacent over hypotenuse. Then multiplying both sides by the magnitude of A, we would get the magnitude of A times the cos of theta equaling the scalar projection of A onto B. Okay? And so that's what we show here. The projection will equal the magnitude of A cos theta. Now, we can multiply top and bottom here by the magnitude of B, and we would get that fraction there. And if you're curious why we would do that, it's because that makes the numerator equal to A dot B. And so we're able to say that the scalar projection of A on B is equal to A dot B times the magnitude of the vector B. Now you might be wondering, but what if the angle's obtuse? There'd be no floor at all. In other words, if I'm trying to drop this down, how would I figure out the length of that? The answer is, again, really seems like cheating perhaps, but we're just going to extend that floor backwards if necessary, drop down that perpendicular, and then we'll be able to calculate the scalar projection. So like it says here, just extend B in the opposite direction, and then we can calculate that. And the scalar projection will be negative, and it works out nicely because the cosine value of an obtuse angle is negative, so A dot B will be negative, and using the same formula we had a minute ago will get us the scalar projection in that circumstance as well. We want a negative number, and since the angle is obtuse, A dot B is negative. So no matter what the situation, we can say the scalar projection of A on B will be equal to A dot B over the magnitude of vector B. And we typically refer to the scalar projection of A on B this way. Scalar projection of A on B as shown there. Okay. Now let's talk about vector projections. We might want to be able to not just determine the scalar projection, but the vector projection as well. So suppose we have vector A and we have vector B, and we're projecting A onto B, and we come up with a scalar projection as indicated with the highlighted line there that I have at the bottom. Well, instead of a scalar quantity, what if I wanted that to be a vector quantity? What if I wanted to determine this vector, putting an arrow right there? How would I do that? Well, fortunately, the scalar projection of A on B gives me the magnitude that I want. But I need a direction without changing that magnitude. The way to get a direction without changing a magnitude is to get a unit vector in the direction we wish to go. Because then when we multiply, the unit vector has a magnitude of 1. So when we multiply our scalar projection of A on B times a vector with a magnitude of 1, we don't change the magnitude. We keep that magnitude, but by putting it in the direction of B, we get the direction that we want. So a vector projection of A on B will be equal to a scalar projection of A on B times a unit vector in the direction of B. Now you might think to yourself, how did we get those unit vectors in previous lessons? What we did is we determined the magnitude of B. So let's say B had a magnitude of 5. We then determined 1 over that magnitude and multiplied it by b. So again, using 5 as our example, if the vector b had a magnitude of 5, we simply would multiply that vector by 1/5, and this would be a vector in the direction of b that had a magnitude of 1. Okay? So, like we say here, we said in one of our earlier lessons that to get a unit vector in the direction of a vector, we simply divide that vector by its own magnitude. Or in other words, we say a unit vector in the direction of b is equal to 1 over the magnitude of b times b. We don't really divide vectors by magnitudes. Instead, what we do is multiply by 1 over that magnitude. So, what we do then is we have a vector projection of a onto b, as we've said now a couple of times, is the scalar projection of a onto b times a unit vector in the direction of b. We know the scalar projection of a onto b is given by a dot b over the magnitude of b. We know a unit vector in the direction of b is given by 1 over the magnitude of b times b. Multiplying these denominators together gives us the magnitude of b quantity squared. But recall that the magnitude of b quantity squared is equal to b dot b. We talked about that earlier as well. So instead of saying a dot b over the magnitude of b quantity squared times b, we can say a dot b over b dot b times b. And so that is our formula for the vector projection of a onto b. So let's do a couple of examples here. Given the vectors a and b as shown, determine the scalar and vector projections of a on b and of b on a. Well, the scalar projection of a on b will equal a dot b over the magnitude of b, and plugging in those numbers here. To determine a dot b, remember, we're just using the component method. So -3 times -2 is 6, 4 times 2 is 8, and 5√3 times -1 is -5√3. And then determining the magnitude of b, we're just using that pretty simple magnitude formula that we have. And doing that, we get actually a numerator of 14 minus 5√3 and a denominator of √9, or in other words, 3. There's our scalar projection of a on b. Now we want a vector projection of a on b, so that's just going to be a dot b over b dot b times b itself. So this is 14 minus 5√3 over 9 times -2 to -1. Now if we want a scalar projection of b on a, that'll be b dot a over the magnitude of a. So that'll give us 14 minus 5√3 over the magnitude over the square root of 100, which is 14 minus 5√3 over 10. And if we wanted the vector projection of b on a, we'd have b dot a over a dot a times vector a. So that would be 14 minus 5√3 over 100 times the vector -3, 5√3. Now, what if we wanted to determine the projections onto an axis? To determine the scalar and vector projections made by a vector with one of the positive axes, simply need to determine the scalar or vector projection of that vector with the associated unit vector, whether that be I, j, or k. So for instance, if I wanted to know the scalar or vector projection of a vector onto the x-axis, I would just have to determine the scalar or vector projection of that vector onto the vector I. So to show you that I would be a sufficient method to use it to project onto the positive x-axis, what I'm going to do is project a given vector onto the vector 1, 0, 0, which is I, or the vector 100, 0, 0. And we're going to see that no matter which of those we use, the actual scalar projection will be the same. So here we go. If we project -374 onto 1, 0, 0, our scalar projection using our formula is -3. Our vector projection using our formula is -3, 0, 0. Now, instead of projecting onto I, what if we project onto 100, 0, 0? We'll still get the same answers, believe it or not. If we determine the scalar projection of this vector negative 3, 7, 0 onto 100, 0, 0, we'll get negative 3. And if we project onto 100, 0, 0, our vector projection will actually still be negative 3, 0, 0. So the point we're making here is that the scalar and vector projections of that vector are the same on 1, 0, 0 as they are on 100, 0, 0, which makes sense. If we have a short floor, we still get the same projection as if we have a long floor. So the moral of that story is that if we're projecting onto an axis, we can simply project onto the unit vector of that axis. So if we're projecting onto the positive x-axis, we just have to project onto the vector I equals 1, 0, 0. Okay. So long as the vector being projected, we're now repeating myself, so long as the vector being projected onto in the first diagram is in the same direction as the vector projected onto in the second diagram, then the projection will be the same. Okay. Therefore, if we are asked to determine the projection of a vector onto the positive x-axis, we can simply project onto the vector I. That was the point of all that. If we're asked to determine the projection of a vector on the negative x-axis, we can project onto negative I. If we're asked for the projection onto the y-axis, we can project onto j. Negative y-axis, we can use negative j. And finally, if we're projecting onto the positive z-axis, we can project onto k. And if we're projecting onto the negative z-axis, we can project onto negative k. Now let's talk about direction cosine. Suppose I want to know the angle made by the vector ABC with the positive x-axis. So imagine the vector ABC shown. We draw it in red. And I want to know the projection made by that on the positive x-axis. So in other words, what I'm looking for is the length of that line. I'm looking for the angle, but to determine the angle, I'd like to know what that the length of that line is that I'm pointing at, and the length of the hypotenuse. I know that there's a right angle here, so if I can determine the length of this line and the length of the hypotenuse, I can say cos theta is simply equal to the magnitude of that line over the magnitude of that hypotenuse, the vector itself, the vector ABC. So we know that there's a 90-degree angle, so that's what we've drawn in, and we know the vector is the hypotenuse, as we said. We see that cos theta is adjacent over hypotenuse. Well, we know that the length of this line here will be A, and we know that the magnitude of the hypotenuse will be the square root of A squared plus B squared plus C squared. And so we can, and we also know, like it says here, if A is negative, then the cosine of the angle with the positive x-axis will be negative, and that's true for obtuse angles. And so we know that the formula that we have here, that cos theta will be A over the square root of A squared plus B squared plus C squared. That will work whether the angle being made is acute or obtuse, i.e. whether the A value is positive or negative. So basically what we're saying here is we have a formula that'll work under all circumstances. And a similar formula is available for both the positive y-axis and the positive z-axis. And we have a convention in math that alpha is the vector that is the angle that a vector makes with the positive x-axis. Beta is the angle that a vector makes with the positive y-axis. And gamma is the angle that a vector makes with the positive z-axis. And if the vector itself is ABC, then we can simply say cos alpha will be A over the square root of A squared plus B squared plus C squared. Cos beta will be B over the square root of A squared plus B squared plus C squared. And cos gamma will be C over the square root of A squared plus B squared plus C squared. So if we want to determine the angle made by a given vector with each of the positive axes, then we can use those formulas. Cos alpha will be equal to negative 2 over square root of negative 2 quantity squared plus negative 6 quantity squared plus 3 squared. And cos beta will be the same denominator but a numerator of negative 6, and cos gamma will be the same denominator but a numerator of 3. Now that denominator, that long thing there, negative 2 quantity squared plus negative 6 quantity squared plus 3 squared is actually equal to 49. So the denominator is root 49, which is 7. So letting alpha be the angle made with the positive x-axis, we see that cos alpha will be negative 2/7. So alpha will be roughly 106.6 degrees. Cos beta, where beta is the angle made with the positive y-axis, will be negative 6/7, meaning beta will be approximately 149.0 degrees. Cos gamma will be 3/7, so gamma will be approximately 64.6 degrees. And so we can say the vector negative 2, negative 6, 3 makes an angle of approximately 106.6 degrees with the positive x-axis, an angle of approximately 149.0 degrees with the positive y-axis, and an angle of approximately 64.6 degrees with the positive z-axis.